So to start today's class, what I want to do is go through second take-home exam 1 problem from 2 years ago's class, which is a new type of problem involving a new type of idea that's hinted at by this star symbol right there. It's called a convolution operator. Being a new idea and being this is the last class before your exam 1, if I put this on your exam 1, it would probably be on the take-home, in addition to perhaps a simulation problem or 2 on the take-home. It's a hard enough idea as well. But once again, in this class, being an applied class, I mean, we're talking about theoretical ideas, though we ultimately want to look at applications. But we don't want to make it too theoretical because it'll just get too hard and sort of beyond the point of the class. So we'll illustrate theory, talk about theory, sort of more in the context of examples than giving a full-blown theoretical treatment of things. So we're example-based. And this does have important applications in real life. What we're after here are looking at the sum of 2 random variables. W is x plus y. And it's also related to chapter 7, and we're going to relate this to the material in the last couple sections of chapter 7, in particular the fingerprint theorem, the fact about moment generating functions of sums of random variables, and the central limit theorem. Try to, after going through this problem, relate this to those. Actually, I want to do one more problem beyond this as well that's related to convolution. Well, let's go ahead and get into this. Let x and y be independent discrete random variables with the following p. Okay, this now I call this PMFs. I'm trying to emphasize that with discrete, even though our book still calls them PDFs because it's an old book, it's more traditional these days to call them PMFs, probability mass functions, because these values of these functions give actual probabilities. You don't have to integrate them to find probabilities. They're not giving you probability densities. So they're independent, and W, yes, is the sum of these 2 variables that are assumed to be independent. That independence assumption is necessary to make the problem easier. If they're not independent, then the problem can become much harder. We want to find the PMF of this random variable W that is the sum of x and y. And remember, with PMFs, probability mass functions, yes, like I just said a minute ago, you plug in numbers into them to find actual probabilities. Their outputs, their values give you actual probabilities instead of probability densities. Right? That's nice with discrete random variables. You don't have to integrate. And this convolution operator thing is just a symbol, okay? It's just a symbol for a way to combine the 2 PMFs for x and y, called f and g, to get the PMF for w, the sum of x and y. I'm calling that PMF H. Okay, so it's like an addition, multiplication symbol, function composition. It's a binary operation. Hey, abstract algebra people, binary operation, a way to combine 2 functions to get another function in this case. So it's just a symbol. How do you actually find it? Let's just take it case by case. This is discrete with finite set where these PMFs are positive, so I can just go ahead and compute some values, essentially fill in a table for the random variable W. What is H of 0? That's the probability that capital W equals 0. Capital W is x plus y. And in this context, since x and y can't take on negative values, they're non-negative random variables. They can't take on negative values because there's the probability that they take on a negative value is 0. The only way this can happen is if x and y are both 0. And there we have the lovely word and in there, which alerts us to using, by the assumption of independence, the multiplication rule. This is the same as the probability that x equals 0 times the probability that y equals 0. Now just look in the table. probability that x equals 0 is the 0.5 right there, 0.5. The probability that y equals 0 is the 0.65. Multiply those, you'll get 0.325. Right? Check my arithmetic. Yes, 0.325. So there's the probability that W equals 0. That's the value of the PMF H at W equals 0. How about H of 1? Probability that W equals 1, which means it's the probability that X plus Y equals 1. Based on the nature of where X and Y can take on values with positive probability, this can happen in one of two ways. You can think of it as a compound event. X equals 1 and Y equals 0, or X equals 0 and Y equals 1. These two events, X equals 1 and Y equals 0 versus X equals 0 and Y equals 1, are definitely mutually exclusive events, right? Disjoint. If one happens, the other can't happen. You don't need to assume they're mutually exclusive. They are mutually exclusive. So by the or there and the addition rule, which is really an axiom for probability, I can say this is the sum of the probability that X equals 1 and Y equals 0 with the probability that X equals 0 and Y equals 1. And there I have, and again, that's the same by the multiplication rule for independent events. I'm assuming independence, remember? If I didn't make that assumption, that's why it would get a lot harder. I'd have to think about conditional probability. I'd have to know some conditional probabilities. Maybe based on some given joint distribution even. I can multiply these probabilities. I didn't write in the first line here these things in terms of F and G, but I could have. This was the same as F of 0 times G of 0 up there. I can write this in terms of F and G. This is the same as F of 1 times G of 0 plus F of 0 times G of 1. In terms of the PMFs, probability mass functions of X and Y individually. Looking at the table, F of 1 is 0.3, G of 0 is 0.65. It's easy to make a mistake here, including me. It's easy to make a mistake, so be careful. F of 0 is 0.5, and G of 1 is 0.25. Don't want to make a mistake. Use my calculator here. 0.3 times 0.65. 0.195, and then 0.5 plus 0.25. I can do that in my head is 0.125. So this gives 0.32. So the first value, the probability that W equals 0 is 0.325. The probability that W equals 1 is 0.32. I could also try to compute the CDF of W. Capital H of 0 would be 0.325, and capital H of 1 would be the sum of these two, would be 0.645. Continue, what about little h of 2? Probability that W equals 2, meaning the sum of X and Y is 2. Using the same kind of logic, the addition rule for disjoint mutually exclusive events and the multiplication rule, we would find that you ultimately get F of 2 times G of 0 plus F of 1 times G of 1 plus F of 0 times G of 2. Why? Because F of 2 means X equals 2. With G of 0, we're referring to the probability that Y equals 0. One way X plus Y can equal 2 is if X is 2 and Y is 0. Another way X plus Y could equal 2 is if X is 1 and Y is 1. And a third way that X plus Y could equal 2 is if X is 0 and Y is 2. So I skipped some steps there. I should have colored that green. Anyway, go back up to the table, be really careful. F of 2 is 0.2 times G of 0 is 0.65. 0.2 times 0.65. F of 1 is 0.3, G of 1 is 0.25. F of 0. I didn't make a mistake, did I? You got to be super careful with not making mistakes here. F of 0 is 0.5 and G of 2 is 0.1. Does it look good? This gives 0.13 plus 0.075 plus 0.05, if I've not made a mistake. .255. Yeah. Yep. Okay. That's the probability that the sum of the two variables is 2. H of 3, probability that the sum is 3. Dots. X plus Y equals 3. Neither variable can equal 3 individually with positive probability. But the sum can be 3. X could be 2 and G could and Y could be 1. Or X could be 1 and Y could be 2. Leave a little space in here. Well, do dots. Leave a little space. Let me write F of 2 times G of 1 plus F of 1 times G of 2. Leave some space there. I'm going to finish the calculation now by looking at the table, but continue leaving space. F of 2 is 0.2. G of 1 is 0.25. 0.2 times 0.25. F of 1 is 0.3 and G of 2 is 0.1. Let's also leave a little space here. What's the final answer going to be? This is going to be 0.05 plus 0.03, 0.08, it looks like. What are we up to here? 0.325 plus 0.32 is 0.645. 0.645 plus 0.255 is up to 0.9. Add on 0.08, we're up to 0.98. Getting really close to 1. There's only one more value W can take on, that's 4, when X is 2 and Y is 2. Why did I leave some space? Because I also could have written F of 3 times G of 0 plus in there. But F of 3 is 0, so it doesn't affect anything. And I also could have written plus F of 0 times G of 3. But G of 3 is 0, so it doesn't affect anything. Why did I do that? Because it fits the pattern better, hinting at the more general formula for the convolution of two non-negative random variables. Let's do the last case, h of 4. Dot, dot, dot. Let's just write it with some space in here as f of 2 times g of 2. If x is 2 and y is 2, then the sum is 4. And f of 2 times g of 2, looking at the table, I won't bother showing you, is ultimately 0.2 times 0.1, giving us 0.02 as it had to be if this is the last value, possible value of x. Remember, we were at 0.98 for the sum of these probabilities, so this brings us up to 1. What would go in the space there? How about f of 4 times g of 0 plus f of 3 times g of 1. I want the inputs to add to 4 over here, plus f of 1 times g of 3 and plus f of 0 times g of 4. But those are all zeros because this is 0, this is 0, this is 0, and this is 0. So I don't have to put them in there, but it's nice to put them in there to emphasize, again, the pattern. In each case, whatever the input is for h, I add up products of f and g where the sum of the inputs for f and g have to add to that value that you're plugging into h. In this case, 4. Where the sum ranges over, focus on the inputs of g, the input of g, say, going from 0 up to whatever the number I'm plugging into h is. So it seems to be the pattern is that h of w, the convolution of f and g evaluated at w, discrete convolution, there's a continuous convolution as well, that maybe I will talk about next Tuesday before spring break. After going over your exam, maybe I'll talk about the continuous convolution, though I probably won't test you on it ever, but just to inform you about it. The formula seems to be add up, say as k goes from 0 up to w, f of, let's see, the input of g is going to be the k. That starts at 0 and goes up to w. If you look at the pattern here, the input of f would have to be w minus k. Although it is symmetric, we could think of the summation in the opposite order. This does equal the summation k goes from 0 to w of f of k times g of w minus k. When I think of it the first way, I'm thinking of the summation that you see here from left to right. When I think of it the second way, I'm thinking of the summation going from right to left. Essentially, it's the commutative property of addition that allows you to write it either way. Let's apply this idea in the more general form to a problem that is technically harder, but I think with enough being careful, we can do it. Let's add 2 Poisson random variables. Could just show up on the test. I'm not ruling it out, I guess. Poisson is discrete, right? X, let's assume X is Poisson. What did Poisson variable, what were they about? They were in chapter 3, it's a discrete random variable that counts the number of occurrences of something over some time interval or in some region, some area, or maybe some volume. A common kind of example would be in, say, an insurance application is to count the number of earthquakes of a certain magnitude in, say, Los Angeles over every decade or something like that. Maybe how many earthquakes are there somewhere in Los Angeles of magnitude, I don't know, 4.0 or greater every decade. I imagine there's at least one, maybe two. That kind of situation where you make a count of how many of those things occur over a certain amount of time is an example where people commonly try to use a Poisson random variable to do the counting and to do the modeling. So it's a very well-used kind of distribution. Let's assume X is Poisson with mean 2. That's the thing that's called K in the book, or lambda times S. You had some homework problems where you were using Poissons recently, so you had to look it up. S is typically taken to be the, well, you got a certain unit of time, for example, maybe a year, maybe 10 years or something. And S counts the number of those time periods, and lambda is the number of occurrences per time period. For example, if you were focused on S being counting the number of years, and then your ultimate focus is on the number of earthquakes per decade, then lambda would be the number of earthquakes on average per year, and then S would be 10 years in a decade. And then K would be the average number of earthquakes per decade. Okay, don't worry about it. That's just a reminder. And let's say Y is Poisson of mean 3. That's also K for that random variable. And let's probably make more sense to call it S, but I'm going to go ahead and call it W again. Let W be the sum of X and Y. And we'll make our usual assumption that X and Y are independent. By the way, I should have emphasized that I also in the previous problem could have found the means of X and Y and W. And yes, it is true that the expected value, the mean of W, is the mean of X plus the mean of Y. And that's something you've always known since you ever learned chapter 3 in Prob and Stats. And it is true, and you can confirm it with the formulas here. But what I want you to realize is this fact, even though it's a fundamental fact that we always use, because it ultimately refers to convolutions, is not so easy to prove, actually. Even though you've used that all the time in Prob and Stats and this course whenever you needed it, it's actually not so easy to prove. Not as easy as you might hope, because the distribution of the sum is difficult to deal with. Even when you assume X and Y are independent, you still have to do this convolution idea, so it's still a difficult thing to think about. I do want to relate this to chapter 7 here still today, but hang on. So W is X plus Y. Here's our question. What is the distribution of W? What kind of random variable is it? We will address that with chapter 7 ideas more simply using the moment generating function. But for the moment, let's think about it in terms of this new idea, this discrete convolution. And let's go ahead and think about it in the more general formula. Poisson random variables are non-negative. They don't take on negative values, and therefore I can think of the formula this way. When your random variable takes on negative values, then you have to allow for K starting at perhaps some negative value, or maybe even negative infinity when you look at the summation. Yikes. But since our random variable starts with, our random variables only had to take on 9 negative values with positive probability, we can do a simpler version. So H of W, just like before, is going to be the PMF, probability mass function for W. It is this probability. I should use a cursive W to emphasize its lowercase here. And because of independence, that allows me to say, ultimately, that this is a summation of products of the PMFs of X and Y. Same kind of summation that was on the other page. K goes from 0 to W of f of W minus K times G of K, where F and G are the PMFs of X and Y. PMF of X, PMF of Y. Okay, so I guess I need to remind myself the PMF of a Poisson random variable. You can look in the chapter 3 table for that. Right there. E to the negative K times K to the X over X factorial, where K is the mean. It's also the variance. That's not a typical property for the variance and the mean to be equal, but it is for Poissons. So here's that. Here with X, it's with K equal to 2, and with Y, K is 3. For X, K equals 2, so I get the value of little f is e to the negative 2. 2 to the X, but I'm plugging W minus K in for X. So it's really 2 to the W minus K. Ugh. I guess I'm not making my W cursive here. Oh, well. Over W minus K factorial. That's the X factorial. And the G is K is 3, e to the negative 3 times 3 to the K over K factorial. Wow, this doesn't look so easy. But it is doable if you're good enough at algebra, which I wasn't sure I was going to be before I worked on this morning, but then I figured it out. We want to simplify this thing. Doesn't look like it could be simplified, but it actually can. It can be simplified pretty far, actually. One thing you can do is you can factor out, you can combine the e to the negative 2 and the e to the negative 3 to get e to the negative 5. And that can be pulled in front of the summation. It's a constant. And thinking about doing that reminds me, maybe we might be hoping something's true. We might be hoping, praying that maybe W is Poisson. And maybe its mean is 2 plus 3, 5. I mean, insurance companies have to think about this. If X is the number of earthquakes in a decade in Los Angeles and Y is the number of earthquakes in a decade in San Francisco, the sum is the number of earthquakes per decade in Los Angeles or San Francisco combined. If we're modeling X and Y as Poisson, it sure be nice if their sum is Poisson, and that'd be nice and simple, and maybe it's true, at least if you assume independence. And the answer is yes, it actually is true. We will get that. It'll be a Poisson random variable with a mean of 5. So that gives me hope in seeing e to the negative 5. The final answer has got to involve e to the negative 5, and there it is. Well, what do you do with all the rest of the stuff? Once again, I'm kind of hoping that the answer is a Poisson with a mean of 5. What would the PMF of a Poisson with a mean of 5 be? I'm hoping I can simplify it to this thing when K is 5. I've already got the e to the negative 5. I'd have to get a 5 to the X or 5 to the W and then divide by W factorial. But what about the summation? What's going to happen here? I got the e to the negative 5. Okay, in my quest to realize this hope that this is going to be Poisson, maybe I should try to get a W factorial on the bottom somehow. Because I'd have to have a W factorial at the end there. How? My denominator is this, which does not equal, the product of those two things does not equal W factorial. But I could make this thing become a W factorial if I just multiply the top by the appropriate thing. And I'm realizing I don't have enough space. I could make this be a W factorial on the bottom. How? By multiplying this fraction by an appropriate form of 1. What's the appropriate form of 1? Put the 2 to the W minus K here. The appropriate form of 1 would be W times W minus 1 times W minus 2 dot 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 times W minus K plus 1 over that same product, which I've already included by writing W factorial. Let's move the W factorial over from there so it's more symmetric. The e to the negative 5 on front comes from the e to the negative 2 and the e to the negative 3. Pull that out in the front. It's no longer there. I'm focused on this fraction equaling this fraction. Because to get from here to here, I multiplied by a disguised form of 1. This entire product divided by that same product, which I combine with the W minus K factorial to say it's W factorial. Don't forget about everything else over here as well. Well, I already factor out the e to the negative 3. This over here is just 3 to the K over K factorial. So that's progress, perhaps, because I got a W factorial down there like I'm hoping I can get. And in fact, it's even more progress. W factorial doesn't depend on K. I can factor it out. I'm feeling good. It can be factored out of the summation on the bottom. Because it doesn't depend on K. W is fixed. K is the variable here in the summation. What am I left with? I can't, well, I could factor out individual things here, but I don't want to factor it out, anything individually here. I mean, the end result of all these products does depend on K. Leave those in there. Put this all over K factorial. And then write 2 to the W minus K here and 3 to the K there. Does anybody feel like they know where I'm going with this? Anybody have an gut instinct as to what fundamental fact that you have learned about in the past that I'm going to use here to simplify this a lot? Binomial theorem. This thing right here is W choose K. It may not look like it because you think of W choose K as W factorial divided by K factorial times W minus K factorial. But those are the same thing, because W factorial is the same as all this stuff on the top times W minus K factorial, and the W minus K factorials can cancel. E to the negative 5 over W factorial times the summation K goes from 0 to W of W choose K times 2 to the W minus K times 3 to the K. I just realized I probably shouldn't have used K as my index of summation, because I already used K as the mean of the Poisson. Sorry about that. Up here, K is mean of Poisson. Down here, K is index of summation. The binomial theorem allows us to simplify that summation greatly to 2 plus 3 to the W power. That's the binomial theorem. Right? Usually, 2 and B are letters like A and B or something, or P and Q. But here they're actual numbers. And there we have it. Isn't this beautiful? It's simplified to the PDF of a Poisson with mean 5. And this is valid for W equals 0, 1, 2, 3, etc. If you add a Poisson with mean K1 to a Poisson with mean K2, and they're independent Poissons, the result will be a Poisson whose mean is K1 plus K2. K1 is 2 here, K2 is 3. So a little more practice with the idea of a convolution there. I don't know exactly what I might ask you about it. I'm going to take home, perhaps. Maybe something more like this one. But I thought it was worth doing it anyway. Partially because it's amazing, and partially to highlight the distinction between what we just did here and what you find in chapter 7 with moment generating functions in the fingerprint theorem. Let's do the same problem now. Show that the sum of two independent Poissons, one with mean 2 and one with mean 3, is another Poisson with mean 2 plus 3 equals 5. But now let's use moment generating functions. And with the theorems in chapter 7, the moment generating function approach is easier than what we did with convolution. So once again, X is Poisson with mean 2, Y is Poisson with mean 3, and W is X plus Y, where X and Y are independent. That's just an assumption we're making of independence. Again, it's a modeling assumption. And with California and San Francisco, it's probably actually not the greatest assumption. I mean, they're kind of far away. Well, I mean, Los Angeles and San Francisco. They're kind of far away, like 5 hours drive time, but still they're both close to the San Andreas Fault. So the assumption of independence for Los Angeles and San Francisco is a bit dubious. However, if you compare Los Angeles to Tokyo, okay, then it's more reasonable. The independence assumption is an assumption about modeling that you hope is valid, and you often try to make it, use it if it seems reasonable, though you might want actual hard data to see if it seems reasonable, like are earthquakes in Los Angeles and Tokyo correlated at all? They're not in the San Andreas Fault, both of them, but they are in the same ring of fire around the Pacific Ocean. There's lots of earthquakes. I don't know if you know this, going up through California into Alaska, then down Russia into Japan, and that kind of thing. There's a lot of earthquakes and volcanoes along that path. So seems more reasonable, but not completely unquestionably reasonable. Anyway, let's use the moment generating function approach based on, again, the fingerprint theorem and this theorem, chapter 7. X1 and X2 are independent random variables with known moment generating functions, and Y is their sum. Then the moment generating function for Y is the product, not the sum, the product of the moment generating functions for the variables that you're adding. So that would be true here. The moment generating function for W by independence is going to be, and since W is the sum, is going to be the product of the moment generating functions for X and Y. Look it up in the table. There's the moment generating function for a Poisson with mean k. Kind of strange. Exponentials within exponentials there. E to the k times e to the t minus 1 all is the power of e. Exponentials within exponentials. Bit strange, but that's what it is. K is 2 for x, so I get e to the 2 times e to the t minus 1, and k is 3 for y, so I get e to the 3 times e to the t minus 1, and then just simplify by adding the exponents. Maybe I should distribute the 2 through the first one first, and then the 3 through the second one second, and add those exponents. E to the 5 e to the t, and then minus 5, and then you can factor out the 5. And then you say, hey, that is the moment generating function for a Poisson random variable with mean of 5. Therefore, by the fingerprint theorem, previous page, if two random variables have the same moment generating function for all t in some open interval around the origin, then they have the same distribution. You don't say they're the same random variable, because for given a situation, they could take on different values because of randomness. But you say they have the same distribution, which means they have the same PDF, the same CDF, the same mean, the same variance, etc. Fingerprint theorem now implies that W, which is the sum, is Poisson with mean 2 plus 3. In other words, Poisson with mean 5. Actually, I probably should have written those in the other order. It's Poisson with mean 5, and 5, hey, is 2 plus 3. So yes, I did add the means of the individual random variables. So yeah, once you've got the theorems in chapter 7, the moment generating function technique is easier. Though I will say proving the fingerprint theorem is no piece of cake. The book doesn't even bother proving it at all, not even in the appendix. It's pretty advanced math to prove the fingerprint theorem. Proof is based on transform theory. Even just saying transform theory sounds scary, right? Transform theory. It's related to things like Laplace transforms and Fourier transforms. Essentially, the moment generating function is related to transforms, but I won't go into detail. We're happy to use the theorems without proving them. We're also happy to use the central limit theorem without proving it. So I remind you one more time, as it's stated in the book, it's not really a theorem. Our book is an application-oriented book, probability statistics for engineers and scientists. And yeah, most engineers and scientists and applied statisticians, applied mathematicians are fine with this statement as is and not worried about the fact that it's not precise enough as stated to truly be a theorem that you could prove. There is a version of the central limit theorem that is very precise. You can describe exactly what everything means, and therefore you can prove it precisely. But it goes beyond the scope of our class. So we are satisfied with this as is. If you've got a random sample of size n, so the assumption, underlying assumption there then is these all have the same distribution and they're all independent of each other. Which would mean, here's a question that could come up maybe as true false on the test. The definition of independence, random variables, whether it's two variables or n variables, is related to chapter 5, which I have talked about a bit, but not nearly as much as other stuff. But you should certainly know some facts from chapter 5. For example, one prominent fact to know is the definition of independent random variables. X and Y are independent by definition. This is not a theorem to prove it. It's what it means. If they're joint density in the continuous case or joint PMF in the discrete case is the product of the marginal densities or PMFs for X and Y individually. And effectively, when we assume independence, that means we just assume this equation is true. We don't have to prove it's true in a certain situation if we're assuming it's true. And this does generalize to n independent random variables. The joint n-dimensional density with n variables x1 through xn would be the product of the n marginal densities. And again, if x and y are from a random sample, they would have the same distribution. In fact, the product of these two functions would be the product of a function with itself, except one variable would be called x and the other variable would be called y. But it would be the same formula that would be being multiplied. So I could see that coming up maybe on a true-false question. Some fundamental facts from chapter 5, even though we haven't emphasized chapter 5, you should know fundamental facts like that and what the expected value formulas are and the definition of covariance and this theorem. If x and y are independent, then this is true, though it doesn't go the other way around, which means the covariance, when they're x and y are independent, the covariance is 0. We will actually need the idea of covariance when we get to multiple regression. So it's worth saying, yeah, you should make sure you know those facts, maybe for true, false, or multiple choice questions on the test, on the in-class portion of the test. Probably won't emphasize some other stuff that we did in problem stats so much, at least not in the in-class portion. Conditional densities and the curve of regression, though that is relevant for regression later. Probably won't emphasize it though. Coming back to the central limit theorem, we're assuming the background distribution that we're taking the random sample from has a finite mean mu and a finite variance sigma squared. It's implicitly assuming that those exist. In the continuous case, that the corresponding possibly improper integrals converge. Then for large n, the word large is vague. That's part of what makes this not a theorem statement. X bar is approximately, there's another vague word, approximately normal with mean mu and variance sigma squared over n. So then if you standardize it effectively, subtract the mean and divide by the standard deviation, you get something that's approximately standard normal. This is related to what's going on here a little bit at least. W is not the mean of x and y, but it's close to the mean. It's x plus y. I didn't divide it by 2. I could have. You might wonder what would happen. How would it change if I divided by 2 there? Well, you'd have to ask the question, what would it change if I divide x and y individually by 2? Are they still Poisson? Do I divide the mean in half? You would think so, intuitively. If I do x plus y divided by 2, yes, W would be a mean of x and y, but n is not very large. So you might say the central limit theorem doesn't really apply because it's assuming n is large. But maybe if I was doing a bunch of Poissons added together and then divide by the number to get a mean when n is large, a bunch of Poissons, I'm saying n is large, the central limit theorem should still apply. Well, if I add a bunch of independent Poissons, the answer still should be Poisson with mean equal to the sum of the means. So what this is hinting at is when n is large, the PMF of a Poisson distribution should look approximately normal. Does it? Plot. Let's see, what do we, it's got to be discrete plot because it's a discrete plot. Okay, Mathematica calls it a PDF, but I really mean PMF when I talk about it. Poisson distribution with k degrees of freedom. I guess I'll put this in a manipulate to see how it changes. You can do a histogram version of this too, I think, but this is just going to make a bunch of line segments. So there's the PMF of a Poisson when k is 1. As k increases. Yeah, I mean, it's a discrete distribution, but yeah, the graph is looking more like a bell-shaped curve. Okay. So that, in a sense, is an application of the central limit theorem, illustrating it here with Poissons. You might argue, well, that's discrete, whereas normals are continuous. That would have to be made precise as well. What does it mean to approximate a discrete distribution with a normal? I mean, you've done that a little bit with using normals to approximate binomials with a half-unit correction, right? And I think I may have put that on the exam from 2 years ago in class portion, a half-unit correction problem. So it's something you should know. There's one more thing in chapter 7 we haven't covered, and that is confidence interval. But that's easy enough to compute. You should certainly be able to compute a confidence interval. Let's go ahead and talk about it right now. This is a theoretical result. Those are random variables. X bar is a random variable. But when we actually have a random sample of observed values, then you go ahead and compute these things. Compute X bar, the sample mean. You'd have to know sigma here. This is assuming you know what the population standard deviation is. N is the sample size. Remember what z sub alpha over 2 is. This notation is consistent with the rest of the book. When you put a subscript on the variable name, that's referring to the number on the axis where the area under the PDF, in this case, to the right of that number is whatever the subscript is. Right? And the most common example is a 95% confidence interval, which you write with alpha as 100 times 1 minus alpha percent. So if that equals 95%, that means 1 minus alpha is 0.05, no, 0.95, excuse me. 0.95, so that means alpha itself is 0.05. So alpha over 2 is 0.025, and that means z sub alpha over 2 is z sub 0.025. That's the most famous one, 1.96. Which you probably have memorized, but you could look it up if you needed to. with a table, a standard normal table, you'd be looking for an area, a CDF value of 0.975. 975 right there corresponds to 1.96. And with the calculator, distribution menu, inverse normal. Area meaning CDF value 0.975, mean of 0, standard deviation of 1, 1.96. And you should be able to do that process for other values of alpha, even maybe non-typical ones when you've got your technology here. If I asked you for a 97% confidence interval, technically speaking, with your technology, you should be able to do it. Reminder of what you hope about the confidence interval. You hope it captures the true mean. That's the point, is you're trying to do it instead of a point estimator of the mean, you're trying to do an interval estimator. And so when you look at the observed values, you hope that it captures the true mean. You express that hope as a level of confidence. Does the 95% in a 95% confidence interval mean that there's a 95% chance that the mean mu is in the interval that you computed? Technically not, but betting wise, yes. If somebody knew the true mean and wasn't telling you, then you would make a bet on whether you capture the mean based on the 95%. Technically speaking, when you say something has a probability, you're talking about before you do something. You could say there's a 95% chance that the interval I'm about to compute will contain mu. But once you've done it, all the randomness is gone. So technically speaking, it's not probability anymore. So you use a different word, confidence level. But 95%, you're pretty sure. It's probably in the interval. So that's a bit problematic to say probably, because you're implicitly implying a probability. But it's not a super big deal. Another more official way to say it is when you do repeated random sampling. Random samples of the same size and from the same population, and you're doing a 95% confidence interval each time, about 95% of the intervals will trap the true mean. Yeah, so I think that's straightforward enough that you should be able to do it. Even on, you've done it before in class. You're just talking about it for 7 or 8 minutes. But again, you should practice problems from old exams from chapters 2, 3, and 4, and certainly 7. 5 and 6, you should know facts for true false questions and multiple choice questions. I'm probably not going to have you make stem and leaf plots on the exam or anything, or make histograms. That's not really the point of the class, even though those are important things. I suppose I could put it on the take home, but that's not really a point of emphasis for us. Probably not. CDF method problems like you've had on your homework, practice those. That's been our biggest thing, right? CDF method. Biggest new thing. Do you have any questions? That's a tricky question to answer because different people take different amounts of time. I try to make the test so that the average person finishes maybe with 10 or 15 minutes to spare. What's the next mod time? I could give you a little bit more time as well. Does anybody happen to know? Is it 11 o'clock? Or?
No, I think that's community time.
Community time then. So I could let you go to 11 at least, unless that's objectionable to somebody within the class portion.
Is it going to be shorter than regular in class? Part of it. same length as the-
Probably a little shorter, but it's harder material, so time-wise, it's probably not shorter. Maybe number of pages wise, it's shorter. Aim for 4 pages when I typically do 5 pages for exams. I can't guarantee I'll be 4 pages. Maybe 4 pages and then a 5th page is true, false, and multiple choice. I don't know. Yep, you can use the note card front and back, calculator, and I'll give you the tables, and you can have your books open to the appendices if you need them. So yes, you should bring your book and have them ready. Might be nice when you actually set things up for the exam to put another desk close to you so you can set books and stuff on it. Fortunately, I think we've got enough space for that. All right, send you those links here in a bit. Have a good day.